let's go ahead and get going. So I started this problem. I'm taking it back to some washer method here. I want to find the volume of the solid formed by revolving the region bounded by y equals e to the x, y equals 1, and x equals 2 about the x-axis. This is a pretty straightforward problem. Right, so our region looks like this. So here's our y equals 1 is just a horizontal line that looks like this. Y equals e to the x is an usual exponential function, and it intersects the y-axis at the point 0, 1. And x equals 2 is some vertical line over here. So we're looking at this region. So that's the region bounded by those three functions, and we're going to revolve it around the x-axis. So I'm going to draw a vertical rectangle, right? So our rectangle needs to be perpendicular to the axis of rotation. So if we revolve that around, we're going to get a washer, right? If I do this here, my washer is going to look like I always mess it up when I go this way. Right, there's my washer. And the volume of our washer, as it always is the area of the big circle minus the area of the little circle is not there, times the thickness. And the thickness is dx. The volume of my washer is pi times the large radius squared minus pi times the little radius squared times dx. Factor out the pi. And then the large radius is the function that's further away from the axis of rotation, which is e to the x. Smaller function, the one that's closer to the axis of rotation, is y equals 1. And then we're going to integrate from as far left as 0 to as far right as 2. So our total volume is going to be the integral from 0 to 2. Factor out the pi, bring it out in front. And we got e to the x squared, which is e to the 2x, minus 1 squared, which is just 1. And this is not terrible. Right? The integral of e to the 2x is e to the 2x divided by 2. The integral of 1 is x. And we're evaluating from 0 to 2. So we're going to plug in 2. We're going to get pi times e to the 4 divided by 2 minus 2. And then we're going to plug in 0, and we're going to get e to the 0, which is 1 divided by 2 minus 0. And we could simplify that if we wanted to. I don't think it's super important. But you can write everything as divided by 2. So you have pi times e to the 4th over 2 minus 4 over 2 minus 1 over 2 will be minus 5 over 2. And that would be our final answer. Great, no big deal. Excuse me. It becomes a bigger deal when we want to rotate around the y-axis. So, yeah. So let's go around the y-axis. So now I'm using a horizontal strip. When I rotate that around the y-axis, right, I get again a washer. You don't have to draw the washer, I just like to draw it, so we really okay. The volume of that washer is pi times your big radius squared minus your little radius squared, dy this time. Okay, so what's my outer radius? And my outer radius again is, right, the function that's further from the axis of rotation. That's the function x equals 2. So my large radius is x equals 2. And my small radius is this inner function, right? The one that's close to the axis of rotation, which is y equals e to the x. We're solving for x as a function of y. It's going to be natural log of y equals natural log of e to the x. So x equals natural log of y. And so this is going to be the natural log of y. And the limits of integration are going to be as low as 1. Well, so that's right there. So the volume is going to be the integral, or pi times the integral from, let's fill that in a second. The big radius squared is going to be 4. And the small radius squared is going to be the natural log of y quantity squared. As low as 0. Sorry, not 0, as low as y equals 1. And as high as whatever this point is up here. Well, we know that point there is where x equals 2 and x equals natural log of y intersect. So we could set the natural log of y equal to 2, or exponentiate both sides and get y equals e squared. So that point right there is 2 comma e squared. You also could have figured that out just by plugging in 2 for x there and saying y equals e squared. So that's my upper limit of integration. Okay, now here's the thing. Integrating the natural log of y quantity squared is actually not easy. I mean, I know a lot of this is not easy, big surprise, right? If I was doing this, so someone asked me if we could do an integration by parts question with a definite integral, and this is an example. This is going to be an integration by parts, and it is a definite integral. Here's what I would do. I would break it up into 2 integrals. I would write this as pi times the integral from 1 to e squared of 4 dy minus the integral from 1 to e squared of the natural log of y squared dy. And then to be perfectly honest, I would do the integral of natural log of y squared as an indefinite integral on its own on the side. So let's do it on the side, and we'll come back. I want to do the integral of, what did I have here? Okay, the natural log of y quantity squared. So this is an integration by parts problem, and we only have kind of one option. We're going to let u equal the natural log of y squared, and dv is going to be the rest, which is dy. If you knew, so another option that wouldn't work in usually, like right now, is you could let u equal natural log of y and dv be the other natural log of y. The problem with that option is then you have to know how to differentiate natural log of y. We typically don't know that straight off the top of our heads. You might memorize it, but you might not. So my du here, the derivative of the natural log of y squared is 2 times natural log of y times the derivative of the natural log of y, which is 1 over y. I should point out, right, this is 2 times natural log of y to the first power. Right, we're using the power rule chain rule. My v is going to be just y. So using the integration by parts formula, that's going to be uv, so it's going to be this times that, so y times natural log of y squared minus the integral of this times this. So it's going to be y times 2 times natural log of y times 1 over y. Oh, don't forget the dy. I can cancel a y here and a y here. So now, what I've got so far is y times natural log of y squared minus, I'm going to bring out the 2 times the integral of the natural log of y. And then we have to use integration by parts again. So now, we use different colors to differentiate between them. And here we're going to let u equal the natural log of y. dv is going to be the rest, which is still dy. du is going to be 1 over y, dy. And v is going to be y once again. I think this pen is reaching the end of its life here. Okay, so then we're going to get, this is equal to y times the natural log of y squared minus 2 times the integral of natural log of y is the entire uv minus the integral of v du. So it's going to be uv, so y times the natural log of y minus the integral of v du. Let's simplify this, right? Y times 1 over y dy is just going to be 1 dy. So then we end up getting y times natural log of y squared. Distributing the -2, I'm going to do the -2y natural log of y. The integral of 1 is y, so I get a -2 times a minus y, which is going to be a +2y. No, you cannot use the tabular method for this. Right? This is not one of your y to a power times either sine or cosine or e to the x. Sometimes repeated integration by parts you actually have to do the long way, like in this example. So that's our integral of natural log of y squared. So now we're going to go back to the other side and we're going to plug that in. So we're going to say, okay, this is going to equal, I think I need some more room here. So this is going to equal pi times the integral of 4 is just 4y. And the integral of natural log of y squared we just saw was y times natural log of y squared minus 2y natural log of y plus 2y. It's going to be minus, I literally just said it and forgot already, y times natural log of y squared minus 2y natural log of y plus 2y, I believe. Yeah. From 1 to e squared. So that's how I would do a definite integral with integration by parts. I would do the improper integral, the indefinite integral all on its own, and then I would take my final result. Be like, okay, I know how to integrate this thing. The integral of this is that. So I don't have to write all the limits of integration every single step. And then we can, I would probably distribute this minus sign. So it's going to be a minus this. It's going to be a plus this. And minus this. And then we plug in. So we get pi times 4e squared minus e squared. The natural log of e squared is just 2. 2 times 2 squared plus 2e squared times the natural log of e squared is just 2 minus 2e squared. And then minus plug in 1. Plugging in 1, you get 4 times 1. Natural log of 1 is 0. Natural log of 1 is 0. Minus 2 times 1. Okay. So then I end up getting pi times 4e squared minus 4e squared plus 4e squared minus 2e squared. Those cancel. 4e squared minus 2 squared is just 2e squared minus 2. So I end up with pi times 2e squared minus 2. Or you could factor out the 2 if you wanted to. Let's say it's 2 pi times e squared minus 1. So there's some integration by parts thrown into a washer problem. Questions about anything I've done here? Silence from the audience. Sorry. Okay. Let's do a little bit more integration by parts and then let's move along. Let me see here. I believe, actually, let me double check. Yeah. Okay, let's do 1 or 2 more. So sure. Let's do the integral of brain work. Let's try this integral. the integral of x secant squared x dx. So again, integration by parts. Well, so I should say, is it a u substitution, right? We should usually check to see, or at least think about, can we do a u sub first? Well, it doesn't seem like there's a good choice for u here, right? Letting u equal x, du is dx, but I'm still stuck with secant squared of u. Letting u equal secant squared, the derivative is 2 times secant to the first times the derivative secant. That seems like it's not going to work out either. It's probably integration by parts. It's probably going to be u equal to x and dv equal to the rest. Because again, we have this way of picking what we want for u, right? This acronym LATE, where you pick u to be a log thing if you have one. We don't. You pick u to be a power of x. But we do have a power of x to the first. And then if you didn't have that, you pick u to be the trig thing. And then if you didn't have that, you pick u to be the exponential. This is not always 100% guaranteed to work, but most of the time it works. So du is going to be dx. V is going to be the antiderivative secant squared, which is tangent of x. Okay, so then throwing this all into the formula, we're going to get x times tangent of x minus the integral of v du, which is tangent of x dx. I believe we've talked about the integral of tangent x. The integral of tangent x is negative natural log absolute value of cosine. If you didn't remember that, you could then write this as x tangent of x minus the integral of tangent, which is sine over cosine. Then you can do a u sub, with that u equal cosine of x. Du would be negative sine of x dx. So negative du is positive sine of x. So then we could rewrite this as x tangent of x minus the integral of, let's see, there's my negative du, there's my u, so minus du over u, or plus the integral of du over u. The integral of 1 over u du is the natural log of the absolute value of u. This becomes x tangent x plus the natural log of the absolute value of u, which is cosine of x. So there's another integration by parts problem. Let's look at maybe 2 more examples. Another definite one. So let's do the integral of, sure. Let's do the integral of sure, x to the 5th times the natural log of x over 6 dx from 6 to 10. These numbers might end up sucking, but that's life. Okay, so could be u sub. Probably not u sub. If I try letting u equal, it seems like it's not going to work out so well. It's probably an integration by parts. So let's try letting, let's see. So again, according to my acronym here, what should I be picking for u in this particular problem? Anybody in the chat? What's the right choice for u? Is it x to the 5th? Is it my natural log thing? Good guess, Sarah. But in this particular case, it's actually the natural log thing, right? Our LATE acronym says first we're going to pick a log, and then we're going to pick a power of x. I will mention, just as a contrast, if the problem was, say, the integral from, I'm going to pick the same iteration, 6 to 10 of x to the 5th times e to the x over 6 dx, which would be a terrible problem because you have to do integration by parts 5 times. Well, in fact, maybe we'll do this one in a minute here, but in this problem, you would definitely pick u equal to x to the 5th. Here, we're going to pick u equal to the natural log of x over 6. And then my dv is going to be everything else, which is x to the 5th over 5. X to the 5th over 5, just x to the 5th times dx. Okay, my du, so the derivative of the natural log of x over 6 is 1 over x over 6 times the derivative of x over 6, which is 1/6. And notably, those 6's cancel out. So you just get the du is 1 over x dx. V is going to be x to the 6th over 6. All right. So then here's how you can write it if you actually want to write it with limits of integration the whole way. It's going to be u times v, so it's going to be natural log of x over 6 times x to the 6th over 6 from 6 to 10 minus the integral from 6 to 10 of vdu, which is x to the 6th over 6 times 1 over x dx. Gets kind of nasty. So we can plug our limits of integration here. You say, okay, this is going to be, I really don't want to though. I really want to wait until I've written the whole thing out. So I've got the natural log of x over 6 times x to the 6th over 6 minus x to the 6th over 6 times 1 over x. I can cancel an x there and the x there. So I really have x to the 5th over 6. And the integral of that is x to the 6th over another 6 times 6, so 36 from 6 to 10. And then you can plug in the 10, and it's going to be awful, right? Because I made it up and the numbers are not nice. So you're going to get the natural log of 10/6 times 10 to the 6th over 6 minus 10 to the 6th over 36 minus, and then you plug in 6. Now, the nice thing about plugging in 6 is the natural log of 6 over 6 is the natural log of 1, which is 0. So you get minus 0 minus 6 to the 6th over 36. Again, not a very nice result, but that's okay. Let's talk about this problem I made up just as a contrast. So this problem we could also do, and while it would take 5 iterations of iteration by parts, there is sort of a, I don't want to say a short, well, no, there's a shortcut. There's the tabular method. So for this problem here, even though it looks gross, let's talk about it for just a minute. So if I wanted to do the integral from 6 to 10 of x to the 5th times e to the x over 6 dx. So I'm going to use the tabular method. So I'm going to write my u. My u is going to be x to the 5th. Then I want to write all the derivatives of x to the 5th until I get to 0. So the first derivative is 5x to the 4th, and then the next derivative is 20x cubed, and then 30x squared, and then 60x, and then 60, and then 0. And my dv's are going to be interesting. So my first dv is e to the x over 6. And the antiderivative of e to the x over 6 is going to be, well, I know the derivative of e to the x over 6 would be e to the x over 6 times the derivative of x over 6, which is 1/6. The antiderivative is going to be, instead of multiplying by 1/6, divided by 1/6, which is multiplied by 6. The antiderivative of e to the x over 6 is going to be 6 e to the x over 6. And I'm gonna make sure that I don't get things off. So then the antiderivative of 6 e to the x over 6 is going to be another 6 times e to the x over 6. So 6 squared times e to the x over 6. And the next one's going to be 6 cubed times e to the x over 6. And the next one's going to be 6 to the 4th times e to the x over 6. Next one's going to be 6 to the 5th times e to the x over 6. And the last one's going to be 6 to the 6th times e to the x over 6. And then we would do plus this times this, minus this times this, plus this times this, minus this times this, plus this times this, minus this times this. So it's a pain to write out, but your answer is going to be x to the 5th times 6 e to the x over 6 minus 5x to the 4th times 6 squared e to the x over 6 plus 20x cubed times 6 cubed e to the x over 6. Whew. I think you get the idea. Fine. Minus 30x squared times 6 to the 4th e to the x over 6 plus 60x times 6 to the 5th e to the x over 6 minus 60 times 6 to the 6th times e to the x over 6. Evaluated from 6 to 10. I don't think I need to finish that because it would be really awful, but hopefully that kind of shows you the power of the tabular method, right? You can take a really, really, really lengthy integration by parts problem, you have to repeatedly do it over and over and over again, and not have to do that. Okay. One more integration by parts, and then I think we will talk about, oh, there was a couple of U subs people on. Okay, we'll talk about U sub for a second. Actually, it's a good time to talk about U sub now. So here is, let's look at, say, the integral of, e to the cosine of 3x times sine of 3x. So could be U sub, could be integration by parts. But I'm going to try U sub first. And I'm going to try to pick a U thing that's in one of the usual spots, being stuck somewhere. So I'm going to try letting U equal cosine of 3x. Well, that ends up working, because my du is negative sine of 3x times 3 times dx. So then dividing both of the negative 3, negative 1/3 du equals sine of 3x dx. Well, great. There's my negative 1/3 du. Here's my e to the u. Just becomes negative 1/3 the integral of e to the u. And we're almost done, right? The integral of e to the u is e to the u. Gosh, I keep doing that. It's annoying. Plus c. And then plugging back in u, we get negative 1/3 e to the cosine of 3x plus c. So here's a mixture problem, right? It's a mixture of exponential and trig functions where we use integration by parts. On the other hand, if we have something like the integral of e to the 2x times sine of 3x, this is not going to be a time where we can use substitution, right? There's no good choice for u here that's going to make the other part go away. So instead, we're going to do integration by parts. And this is one of those problems when you have an e to the something times sine or cosine, where you have to do integration by parts twice and you end up back to what you started. So I'm going to let u equal the trig thing, right? Because again, according to the late acronym, I don't have a log. I don't have any power of x. I do have a trig and I do have an exponential. So I should let u be the trig thing because that's coming before the exponential thing. So we'll let u equal sine of 3x. And dv is going to be e to the 2x dx. My du, my derivative, is going to be negative cosine of 3x times 3. And my antiderivative, e to the 2x, is going to be e to the 2x divided by 2, or 1/2 e to the 2x. That's what e is equal to. So this ends up equaling uv, and I'm going to erase this here because I want the room. The uv, so 1/2 e to the 2x times sine of 3x minus the integral of v du. So it's going to be 1/2 e to the 2x times negative cosine of 3x times 3 dx. And typically, we like to factor out any constants here. So I'm going to rewrite this as 1/2 e to the 2x times sine 3x minus a minus will be plus, and a 1/2 times a 3, so 3/2 times the integral of e to the 2x cosine of 3x dx. And then we do it again. We say, okay, I'm going to make the same sort of substitution. I'm going to let u equal the trig thing again, in this case cosine of 3x. My dv is whatever's left, which is e to the 2x dx. My du, my derivative of cosine, is negative. Oh, I made a mistake. You guys let me get away with a mistake. My mistake, sorry, yeah, I know you didn't really let me get away with it. My mistake was I accidentally put a negative sign here. Derivative sign is not negative cosine. Derivative sign is positive cosine. Meaning, this should be positive here, meaning this should actually still be negative here. Because the derivative sine is positive, I know that because I know the derivative cosine is negative. So derivative cosine of 3x is a negative sine of 3x times 3 dx. And v, once again, is 1/2 e to the 2x. Okay. So now we've got that this is equal to, still this part, 1/2 e to the 2x times sine of 3x minus 3/2 times the integral of this, which is going to be the uv minus the integral of v du for whatever I've got here. So it's going to be uv, so it's going to be 1/2 e to the 2x times cosine of 3x minus the integral of v du, which is going to be 1/2 e to the 2x times negative sine of 3x times 3. I'm not going to do some of this, sorry. Not quite enough room here. Negative sine of 3x times 3 dx. Because du is equal to negative sine of 3x times 3. All right, so now here's what we've got. We've got our integral, the integral of e to the 2x sine of 3x dx equal to, let's see what we've got here. 1/2 e to the 2x times sine of 3x minus 3/2 times 1/2 is minus 3/4 e to the 2x cosine of 3x. And then we have a minus 3/2 times a minus another 1/2 times 3. So another, let's see, a minus 3/2 times a minus times a minus times a 1/2 times a 3. It's a minus, a minus, a minus. It's a minus. And it's a 3/2 times another 3/2, so 9/4. Integral of e to the 2x times sine of 3x. And look, we're back to the integral we started with. Some people like to call this capital I. And like capital I equals 1/2 this minus 3/4 this minus 9/4 I, and they add 9/4 I to both sides. I think you can also just add the integral. So if I add this to both sides, so I add 9/4 integral of e to the 2x sine of 3x, and I add it over here as well. These cancel, and you're left with, so 1 of a thing plus 9/4 of a thing, well, 4/4 plus 9/4 is 13/4. So I get 13/4 of my integral of e to the 2x sine of 3x dx is equal to this part right here. 1/2 e to the 2x times sine of 3x. I'm going to erase this here because I'm a little bit out of room. minus 3/4 e to the 2x cosine of 3x. To finish the problem, you would multiply both sides by 4/13. So I'm going to multiply by 4/13 here. That cancels. Multiply by 4/13 here. Let's see. Okay, so those area by parts problems, right, they can be quite lengthy depending on what you've got. For these ones especially, this is like on Lee's homework, this is like problem 12 on his homework. You definitely have to do the same sort of thing where you do integration by parts twice. You get back what you started with, you have to add it over to the other side and then multiply by whatever the reciprocal, the constant is. Yeah, fun times. But let's move on. Because you guys are definitely having a homework that has partial fractions on it. Let's go ahead and talk about partial fractions. Actually, before we talk about partial fractions, let me remind you of a couple things, because this is going to come up a lot in partial fractions. We know the integral of 1 over x is the natural log of the absolute value of x plus c. More generally, right, if I said like, what's the integral of 1 over 2x plus 3? You could do a u sub, but you don't have to do a u sub. You say, I know that this is going to be the natural log of the absolute value of 2x plus 3, except not quite. So if I took the derivative of this, I would have to multiply by 2. Right? I would get the derivative of this would be 1 over 2x plus 3 times the derivative of 2x plus 3, which is 2. I don't have a 2 there, right? I just have the 1 over 2x plus 3. I don't have the times 2, so I need a 1/2 to account for that. Similarly, if I was going to do the integral of, say, I don't know, 1 over 5 minus 6x, I know the integral of that is going to be the natural log of the absolute value of 5 minus 6x, except the derivative of this would have me multiplying by a -6. I don't have a -6 on top that I'm multiplying by, so I need a -1/6 to account for that. Or just like we learned way back earlier in the quarter, right? When you antidifferentiate a thing, if the derivative would have you multiply by a constant, your antiderivative would have you divide by that same constant. So that's what we're doing here. And it's going to come up when we do partial fractions. So yeah. Whenever you integrate, like very, very generally, if you're integrating 1 over mx plus b, right, a linear function of x, a line is 1 over a line, your antiderivative is always going to be 1 over that slope times the natural log of the absolute value of mx plus b. Always works. All right, so let's get to the harder things here. Partial fractions, like many of our methods, is a way of making a complicated thing less complicated. So I want to integrate, for example, 2x plus 5 divided by x squared plus 6x plus 8. And I would definitely think about trying to use substitution, but it's not going to work. If I let u equal the denominator, my du is 2x plus 6. So close. You could, it's not really worth it, but some people like to say, well, I'm going to write this as the integral of 2x plus 6 minus 1 over x squared plus 6x plus 8. And then break this up as like this part minus that. You don't want to do this. Not that it doesn't work, but you're just making more work for yourself, because this part you're still going to have to do partial fractions for, and this part over here is going to be an extra u substitution that you wouldn't have to do if you just did partial fractions from the get-go. So partial fractions. There's a couple requirements to be able to use partial fractions. The two requirements are requirement one. Yeah, well, actually, I should say really three requirements. So the first two requirements are that you have a rational function, meaning it's a polynomial on top and a polynomial on the bottom, and the degree on top has to be strictly less than the degree on the bottom. So those are the two requirements. The third requirement after those first requirements have been met is you have to be able to factor the denominator. And this does factor. We can totally write 2x plus 5 over x squared plus 6x plus 8 as 2x plus 5 over x plus 2 times x plus 4. Okay, so now here's the idea. We're going to write this as some number that we don't know yet divided by x plus 2 plus some other number that we don't know yet divided by x plus 4. This is totally going to work because look what, because basically the idea here is that we're saying, well, these fractions have the common denominator as x plus 2 times x plus 4. So if we were to actually add these together, I would multiply this by x plus 4 over x plus 4. And I would multiply this one by x plus 2 over x plus 2. And then, since the denominators are the same, I can just say, well, if the denominators are the same, then the tops have to be the same. So I can say that 2x plus 5 has to equal a times x plus 4 plus b times x plus 2. Now, at this stage, a lot of people do a lot of different things. I personally am a fan of what I like to use, what I like to call convenient values of x, meaning pick values of x that is going to make something equal to 0. What could I pick for x that's going to make this part 0? I should be more clear. These things have to equal each other no matter what value x has, which is why we're allowed to pick any value for x. Right? We're saying this is equal. Doesn't matter what x is, this always has to be equal. So if x is, say, for example, -4, then I can plug in -4 for x here and get 2 times -4, which is -8 plus 5, so -3. If I plug in -4 here, a times 0 is going to be 0, and you're going to get b times -4 plus 2, which is -2. So then solving for b, sorry, that was really itchy. Solving for b, you get -3 divided by -2, so 3/2 is equal to b. Okay, somebody tell me, what choice can I make to make this part here equal to 0? What am I going to let x equal? It's not a trick question. Thank you. Appreciate it. So x equals -2. I'm going to plug it in wherever I see an x. So -4 plus 5 is 1. A times -2 plus 4 is +2. So a times 2. And b times -2 plus 2 is 0. So I end up getting a equal to +1/2. So it is in fact true. I really want you guys to see this. That 1/2 divided by x plus 2, which is a over x plus 2, plus 3/2 divided by x plus 4, this really is equal to 2x plus 5 over x plus 2 times x plus 4. You don't need to show it, but it is true. I could show it, and I would show it by doing the work I already did. I would multiply this by, let's go ahead and do it, right? We're already here. I would multiply this by x plus 4 over x plus 4, and I would multiply this by x plus 2 over x plus 2. When I do it on top, so I get 1/2 times x plus 4, which is going to be 1/2 x plus 1/2 times 4, which is 2, over x plus 2 times x plus 4. Plus 3 halves times x plus 2 is going to give me a 3 halves x plus 3 times 2 is, sorry, 3 halves times 2 is 3, divided by the same denominator, x plus 2 times x plus 4. And oh yeah, look, 1/2 x plus 3 halves x is going to give me 2x, and 2 plus 3 is going to give me 5 over the same common denominator. So hopefully everyone is somewhat convinced that we are really allowed to do this. If you can take a rational function where the degree on top is less than the degree on the bottom, and the bottom factors, you can then break that fraction up into simpler fractions with each separate factor. And then we can solve for the constants that go on top. Okay. So now that we've done all the algebra, we actually want to do the integral. So I'm going to take my integral and say, well, I'm going to replace 2x plus 5 over x squared plus 6x plus 8 with a over x plus 2 plus b over x plus 4. So I'm going to, I guess I write it on the other side here, sure. What I'm going to say is my integral of 2x plus 5 over x squared plus 6x plus 8 is equal to the integral of 1/2 over x plus 2 plus 3 halves over x plus 4. Okay, and now we know how to integrate these things. If you want, you can do more work, but so I'm going to show you the answer, and then I'll show you one intermediate step. I would say that the answer is the integral of 1/2 over x plus 2 is 1/2 times the natural log of the absolute value of x plus 2, plus the integral of 3 halves over x plus 4 is 3 halves times the natural log of the absolute value of x plus 4. If you really want an intermediate step, the intermediate step would be to say, okay, this is going to be, I'm going to break this apart as the integral of 1/2 over x plus 2 dx plus the integral of 3 halves over x plus 4 dx, and then bring out the constants. So that this is 1/2 the integral of 1 over x plus 2 plus 3 halves the integral of 1 over x plus 4. Yeah. So that's our answer. 1/2 natural log of x plus 2 plus 3 halves natural log of x plus 4. Are there questions about that before we do more? Sorry, one sec. Okay. No questions? We're going to do more. Oh, partial fractions. Seems like algebra 6. Yes, it is super. So someone wrote, the concept doesn't seem too hard. It's not too hard a concept. It's really just algebra, right? You're just saying, I can do algebra to make this easier. The issue is it can be really easy to make a mistake with the algebra. So let's do some more examples. Let me take a look at one thing here. Yeah. Okay. So yeah. Where'd you go? Examples. Already, let's get a little bit. Sure. So let's look at another example. I'm going to make something up, which means the numbers might not come out super nice. Let's say, so to the integral of x squared plus 1 over x cubed minus x. So definitely meets all the requirements. Is a rational function, degree on top is strictly less, and the bottom does factor. So we want to factor the bottom. We can factor out an x. And then we can, so let's see, we can write this as the integral of x squared plus 1 over x times x squared minus 1. And it should be more specific. We want to factor in as much as possible. So x squared plus 1 over x times x minus 1 times x plus 1. So this is going to have three pieces to it. We're going to say that this fraction, x squared plus 1 over x times x minus 1 times x plus 1 is equal to a over x plus b over x minus 1 plus c over x plus 1. Now, I showed a lot of work for the previous one. I'm going to show less work here because I want to show you guys kind of the most efficient way to do this. Typically, the next step is to multiply everything by the common denominator. I'm going to multiply both sides of this equation by the denominator x times x minus 1 times x plus 1. That's going to leave me with, let's see. So obviously on this side, I'm just going to get x squared plus 1. If you multiply a fraction by its denominator, you just get the numerator. When I multiply it by the a term here, the x's will cancel. And I'll get a times x minus 1 times x plus 1. When I multiply it by the b term here, the x minus 1's cancel, and you get b times x plus 1. So one more thing. It's getting hot in my office. I need to turn on the AC. All right, cool off a little bit. And then when I multiply this by the third term, the x plus 1s will cancel, and I'll get c times x minus 1. All right, and we're going to go back to our playbook of picking convenient values of x. What's one convenient value of x, somebody? When I say a convenient value of x, I mean a value of x that will make one of these things 0. Yeah, 1, perfect. X equals 1 will definitely make, really, I should be more specific, it's actually making all of them 0 except for one of them. So if I make x equal to 1, on the left side I get 1 plus 1, which is 2. On the right side, I get a times 0. I get c times 1 times 0, but I get b times 1 times 2. So I end up getting b equal to 1. Great, what's a different convenient value from somebody else? I know you guys are there. I know you know what it is. What's going to make one of these things 0? Thank you. Yeah, 1 or negative 1 or 0. So I'm putting x equal to, say, 0. I get 0 plus 1 on the left. On the right, I get, so this is going to be a times negative 1 times 1. This will be b times 0 plus c times 0. So I get negative a equal to 1. So a is going to equal negative 1. All right, and then picking the third convenient value, x equal to negative 1. I get negative 1 squared, so still 1 plus 1 is 2. On the right side, a times that's going to be 0. B times that's going to be 0. And c times negative 1 times negative 1 minus 1, which is negative 2. So I get 2c equal to 2, so c is equal to 1. Great, that turned out pretty well, actually. So now I can say that this integral is equal to the integral of a, so negative 1 over x, plus b, which is 1. 1 over x minus 1 plus c, which is also 1 over x plus 1. And then that's really easy to integrate. That's going to equal negative natural log of the absolute value of x plus the natural log of the absolute value of x minus 1 plus the natural log of the absolute value of x plus 1 plus c. You might see somebody put this all in one natural log. and say it's the natural log of the absolute value of x minus 1 times x plus 1 divided by x. It's the minus there. It's not absolutely necessary to do this, but you might see someone do that. All right, let's do more examples. Actually, yeah. So sometimes other things come up. Sometimes it's not gonna be super easy. So let's look at another example. Let's look at, say, the integral of 3x minus 8 over x cubed minus 4x squared. So this one also factors. This 3x minus 8 over x cubed minus 4x squared factors as 3x minus 8 over x squared times x minus 4. And here's the issue. For this one, we actually need 3 terms. So we need a over x minus 4, and we need b over x squared. But when you have like a term to a higher power like that, you also need every lower power of it as well. So you also need a c over x. Just to show you another example before we do this one. So this other example I'm going to show you we're not going to do. But for example, if I had a problem that was something wild, like the integral of x squared plus 1 over x minus 2 to the 4th times x cubed times x plus 5, which would be a completely heinous, terrible problem. But the way you would start the setup for it would be the following. You have x squared plus 1 over the disgusting bottom, which is already factored for us. And here's what it would look like. It would look like you'd have a over x minus 2 to the 4th, and then every lower power of x minus 2. So you'd have b over x minus 2 cubed, c over x minus 2 squared, and d over x minus 2. And then for x cubed, you'd have e over x cubed, and then every lower power of it. So f over x squared, g over x. And then for x plus 5, since x plus 5 to the first, you only have that. No one in their right mind would give you this problem, or me, right? This is a dumb problem. But the point of this is just to show you that if you have some linear term, meaning x plus a number or x minus a number, or just x itself, or 3x plus 1, right? Or something that's some mx plus b raised to a power, then you need that power, you need your linear term raised to that power, and every lower power until you get to the first power. Hopefully that's not too challenging to kind of conceptualize it. The reason we need this is because these 3 fractions still have this as a common denominator. That's why we need this other term, because maybe, right, if you, in fact, it's actually true that if you didn't have this, it wouldn't work out. Here's why. Let me show you. Let's pretend for a minute that we didn't have this. And if I'm going to do the same thing I did for I multiply this by x squared over x squared, and this by x minus 4 over x minus 4. Here's what's going to happen when I multiply this out. I'm going to get ax squared plus and like is it gonna work out? Plus bx, no, it's not gonna work out. Minus 4b all over x cubed times 4 minus 4. Here's the problem with this. This is supposed to equal this. So a is going to be 0, that's fine. But then b has to be 3 to have a 3x. But b also has to be 2 to have a negative 8. So the problem here is that without that last term there that I need, the A and the B values, the B value can't be both 3 and 2 to make this equal each other. So we need the rest of the terms to make this, so this algebra will actually work out. So someone asked me if the x1 is higher than 1, like we have here, you put it in ascending order, not descending order. The order doesn't actually matter. In fact, the reason I wrote it in descending order was so that it was clear that, okay, we have, like I'm looking at what I have there because it's easier to see the x squared, and then I write all the other lower powers of it. But normally, if I was doing it, I would probably actually write it as I need b over x, and then I need c over x squared. But it literally doesn't matter if you write b over x and c over x squared, or b over x squared and c over x. It's still the same work. It's your answer, your way of writing it might just look different than someone else's slightly, but your final answer, assuming you've done the work correctly, should be the same as anyone else's, even if they write b over x and c over x squared. So it does not matter which order you write them in. Yeah. But I do think, I personally, I like to write it the other way, but I think it's actually easier to see what you're doing through this. So like this, and okay, I see an x minus 2 to the 4th, and then I need every lower power. I see an x cubed, and then I need every lower power. So I think it works nicer that way, kind of. Okay, so let's do the partial fractions part. So I'm going to multiply this by a common denominator. So multiplying everything by x squared times x minus 4. The whole point of this is to cancel out the entire denominator, right? On the left, you're going to get 3x minus 8. On the right, you're going to get a times x squared, because the x minus 4 is canceled. You're going to get b times x minus 4. And you're going to get c times x minus 4. All right. So now we're going to pick convenient values. The problem here, and this is always true when you have a repeated linear factor, meaning something like x squared or x minus 4 cubed or whatever, is you're going to run out of convenient values before you find all your a, b, c's, whatever's. That's all right. So let's pick the convenient value x equal to 0. And if you hadn't noticed yet, your convenient values are just the things that make one of these denominator things here. So 0 makes these 0, 4 makes these 0. So those are my convenient values here. If x equal to 0, I get negative 8 on the left. I get 0 plus b times negative 4 plus c times 0. So negative 4b equals negative 8. So b is equal to 2. All right, let's use our other convenient value, x equal to 4. If x is 4, 3 times 4 is 12 minus 8 equals a times 4 squared is 16a plus b times 0 plus c times 0. So 16a equals 4, so a equals 1/4. Okay, but now I've run out of convenient values. There's two really decent options at this point. One option, which is not my preferred option. And then, so I should say, if you've run out of convenient values and there's only one thing left to find, right? We have b, we have a, we want to find c. There's only one thing left to find. You can pick any other value there. So you can pick x equal to 1. You can plug it in, like 3 minus 8 is negative 5. And then you're going to have 1/4 times 1 plus 2 times 1 minus 4 plus c times 1 times 1 minus 4, and you can solve for c. That's not the way I prefer to do it, though. I prefer a method called equating coefficients, which is where you ask yourself, how much of x to a certain power do I have? Here's the thing. These are polynomial equations. For them to actually be equal all the time, the coefficients have to be the same, meaning how much x squared do I have on the left side here? Well, on the left side, I have 0x squared. On the right side, how much x squared do I have? Well, I have an a times an x squared. I don't have a b times an x squared. If I multiply this out, this is c times x squared minus 4x. I would definitely have a c times x squared. Well, here's what this tells me. This tells me that 0 has to equal a plus c. But I know what a is. That means c has to equal negative 1/4. So again, right, I said if there's 0x squared on the left, there has to be 0x squared on the right. Since I know I have a 1/4 x squared here, c has to be a negative 1/4, so I get a negative 1/4 x squared here, and the x squared all cancel. And now I've got all my coefficients. So don't stop there, right? We still have to do the integral. So 3 always run out of room. So right. So we have the integral of 3x minus 8 over x cubed minus 4x squared dx, and it was equal to what? A over x minus 4 plus b over x squared plus c over x. We just figured out that a was 1/4. B was, I forget what B was. B was 2, and C was negative 1/4. Okay, 2 of these are really easy. The integral of 1/4 over x minus 4 is 1/4 times the natural log of the absolute value of x minus 4. Actually, they're all pretty easy. Just don't get fooled here, right? This is not going to be 2 natural log of the absolute value of x squared. The integral of this, well, this is 2x to the minus second. And the integral of that, we can just use the power rule. That's going to be plus 2x to the negative 1 over negative 1. And then finally, this is going to be minus 1/4 natural log of the absolute value of x. Let's see. Anyway, so you could rewrite this if you wanted to as negative 2 over x. That's what we need to. I'll look at a couple more things. We got time for at least one more. I don't want to do that one. I mean, I do want to do that one, but I want to show you guys one where, sure. We'll do one like this. So someone asked me one of the harder looking ones, or just more complicated looking ones. I'm not going to get to that one today, but maybe we can look at it on Thursday. But here's an example of, yeah, let's look at this one. Let's look at the integral of, I had a better example somewhere. No, I guess not. Okay. Let's look at this one. X cubed divided by x squared minus 4. So it definitely is rational. The denominator definitely factors, but the degree on top is not less than the degree on the bottom. So here's the thing. When the degree on top is larger, before you can do anything else, really, what we're going to do is we're going to do polynomial division. Before I forget, I should take a screenshot of who's here. One moment. Okay. So I'm going to divide x cubed by x squared minus 4. And I'm going to fill in the missing terms. I'm really going to have x cubed plus 0x squared plus 0x plus 0. And it's going to be x squared plus 0x minus 4. So you multiply by x squared to the x cubed, you multiply it by x. X times x squared is x cubed. X times 0x is 0x squared. X times minus 4 is minus 4. Actually, this problem turns out to be a little bit too easy. So we subtract x cubed minus x cubed is 0. This minus 0. 0x minus 4x is 4x. So this is actually just a one step in that we're going to rewrite this as the integral of x plus 4x over x squared minus 4. And in this case, so this is why it's good to do this as well. We actually don't have to use partial fractions here, right? We're going to have a u substitution there. So here, we can let u equal x squared minus 4. Your du is going to be 2x dx. So 2 du is going to be 4x dx. So we can rewrite this as the integral of, well, the integral of x is just x squared over 2 plus the integral of 4x dx, which is 2 du over u. So that's going to be x squared over 2 times 2, sorry, plus 2, now it's all the absolute value of u, plus c, which is x squared over 2 plus 2, natural log of the absolute value of x squared minus 4. So even though sometimes they look like they might be partial fractions problems, they actually end up not being. But let's go ahead and look at a more interesting example, because I feel like that example is not the most exciting. All right, so here's a terrible one that was on someone's homework. We might not finish this, but we'll definitely get started. So here is the awful looking problem. It's the integral of 3x to the 4th plus 27x cubed plus 77x squared plus 84x plus 48 divided by x cubed plus 8x squared plus 16x. Usually, if something looks this awful, it means someone took the time to make sure it turned out nice. That would be true if a human had done this, but since I don't think a human did, it might suck. But we have to do the polynomial division first. So we're going to do our x cubed plus 8x squared plus 16x divided into 3x to the 4th plus 27x cubed. This is gross. Okay, what do you multiply by x cubed to get 3x to the 4th? 3x. And you multiply 3x times that is 3x to the 4th. 3x times 8x squared is 24x cubed. And 3x times 16x is 48x. Subtract 0. 27 minus 24 is 3x cubed. 77 minus 48 is going to be 29. Bring down the next term. Repeat the process. So then what do you multiply by x cubed to get 3x cubed? Oh, 3. Ah, no, that can't be right. No, it can't be right. I just, sorry. 3 times x cubed is 3x cubed. 3 times 8x squared is 24x squared. 3 times 16x is 48x. Subtract. 29 minus 24 is 5x squared. 84 minus 48 is going to be 36x. And then bring down the next one plus 48. Okay. X cubed plus 8x squared plus 16x does not go into that. So that's our remainder. So here's what we get to say so far. This integral is equal to the integral of 3x plus 3 plus the remainder 5x squared plus 36x plus 48 divided by this terrible, oh no, this is not specific, this x cubed plus 8x squared plus 16x. Okay, so then we definitely know how to anti-differentiate this part. We have to deal with this, and we're going to deal with this with partial fractions. So here's our setup. We have 5x squared plus 36x plus 48. I should double check one thing. 5x squared plus 36x plus 48 divided by x cubed plus 8 squared plus 16, which factors as x times Ooh, does it factor? Yeah, x times x plus 4 times x plus 4. That's x cubed plus 8x squared plus 16. It would be a good idea to just, I'm pretty sure we can't, but it's worthwhile to check. Could I do a u substitution here? Could I let this equal a u? Well, if I did, my du would be 3x squared plus 16x plus 16. So let me ask you, is this top part an exact multiple of that? And the answer is no, because to get from 16 to 48, you have to multiply by 3. But 3 times 16 does not give you 36, and 3 times 3 does not give you 5. So no, my du is not an exact multiple of what I have on top. So the u sub is not going to work out. So then we have to write that our fraction is equal to a over x plus b over x plus 4 squared plus c over x. Multiply both sides by the common denominator. So we get 5x squared plus 36x plus 48 equals, so you multiply all of this by this common denominator here. The x is canceled for a, so you get a times x plus 4 squared. The x cancels for b, so you get b, oh sorry, no, that's right. The x plus 4 squared cancels for b, so you get b times x. And 1 of the x plus 4 cancels for the c, is c times x times x. All right, so then if you let x equal 0, you get 0 plus 0 plus 48 equal to a times 4 squared, so 16a plus 0 plus 0. If you let x equal -4, that's going to be fun. So 5 times -4 squared, 5 times 16 is 80. 36 times -4 is 144, negative. And 48 is 48. It's going to equal a times 0 plus b times -4 plus c times 0. So let's see. That's going to be -96 plus 80. So that's going to be -16 equals -4b. So b also equals 4. How about that? And now, to figure out c, here's what I'm going to do. I'm going to equate coefficients. So let me show you guys. If you multiply this out, you would have a times x squared plus 8x plus 16. If you multiply this out, you'd have c times x squared plus 4x. So I know I have 5x squared on the left. And on the right-hand side, I'd have a times x squared. Plus, I don't have any b times x squared, but I do have a c times x squared. But a is equal to 4, so c has to equal 1. Whew. So then we would have this integral here would be 3x squared over 2 plus 3x plus the integral of that, which is the integral of 4 over x plus 4 over x plus 4 squared plus 1 over x plus 4. And then you could integrate that, which is a giant pain in the butt. I mean, the whole problem. So the nice thing about this is the numbers did come out nice, right? You don't have ugly fractions as your constants, but it's still right. So when you have a rational function like this and the degree on top is greater than or equal to, you have to do this process. I want to point out, I know we're out of time, so let me say one last thing. If you have a problem like this, like the integral, say like x squared plus 1 over x squared minus 1, you do want to do the polynomial division here. So for the third value, I didn't plug in an x squared partial for the third value. I asked, and this is the equating coefficients. I asked, how much x squared do I have on the left? Or really whatever my highest power of x is, rather than actually. How much x squared on the left? Oh, there's 5x squared. how much x squared on the right? Oh, there's a times x squared and there's c times x squared. So there's a plus c x squared on the right. And then those have to equal each other because these polynomials are equal to each other. So that's what's going on there. We'll talk, but so for this problem, you would want to do the polynomial division, which would be like x squared minus 1 into x squared plus 1. Anyway, we'll talk more about this on Thursday.